Morning, welcome to our talk, everyone. Today, we would just like to go through atomic rights, what they are, and why are they an important feature for databases. Atomic rights can single-handedly help us get up to 20 to 30% improvement in modern databases like Postgres and MySQL. So, we would just like to run through what they are, what are the challenges of implementing them in the Linux stack, why are they a big deal, and things like that. So myself, Ojaswin, I am joined here with my colleague Ritesh, who is also a co-speaker. And we couldn't be in the conference physically, unfortunately, but we would still like to be grateful to Everything Open for giving us a chance to pre-record our session so that we could still get this to you guys today. So moving on. Yeah, so let's just start with atomic rights, what they are, why are they needed, things like that. So before I start talking about atomic rights, I want to take you through where they are. I mean, how the databases like Postgres right now journal their data or log their data, and where atomic right comes in and how it would help this process. So to go through that, if we can just quickly go through the write ahead logging in PSQL, that would be great. So let's start. So imagine a very simple SQL query. Insert B into table and then you commit. So basically we are just adding some data into the table. That's just what we are doing. And let's go through the flow of how that happens. So our databases, they don't maintain data in terms of very small quantities. They usually have something called a block size, or what I'm calling here a chunk size. So for example, in Postgres, the chunk size would be 8 KB. And so what happens is when I ask Postgres to insert some data into a table, it will try to locate where that chunk, where the data needs to go, where is it located on the hard disk. So as you can see right now on our hard disk, the chunk is somewhere and it has located it. And now it will get the chunk into the in-memory buffer. So the chunk already has some data element called A inside it. Now we want to add B into it, right? So what we do is we add B to the chunk, which is still in memory. Obviously, we don't always write to the hard disk immediately. We keep it in memory so that it's faster. And now what we'll do is, before writing to the hard disk, we will actually add it to a write ahead log file, also known as val file, which is the log of Postgres. And this is an on disk file. As soon as we commit it, it is written on disk. So you can see it as this way. Whatever data is inside the log is actually final. So even if there's a crash at this point, Postgres would be able to recover whatever data is inside the log. So that's what exactly we are depicting here. So as soon as we have written it to the log, we encounter a crash. So as you can see, the data is still in memory. It has not been written to the hard disk. And as soon as system crashes, we lose the upper chunk of 8 KB of data. We just have the log that is persistent on disk. So why do we do this? Let's see the advantage of this log. How can we use this to recover from this crash? So now coming back to log recovery, let's start at the very left. So if you look at the red highlighted box, Postgres would see that, okay, there has been a crash. The database is in an inconsistent state. So it would go and check the log now. And it sees, okay, B is there. B is something that is in the log, and that I need to write that back into the database to make it consistent. So what it will do is it will get the B chunk, and now it needs the initial chunk where it needs to write B. So again, it will go to the hard disk, find the chunk where A exists, get it to the memory, the same step it did last time. This time it would write B from the write ahead log, and it will finally go and write B to the hard disk. Correct. So this is perfect. We crashed in between, but still we were able to get our database into a consistent state because of the log, right? Now, I would like to take you through a scenario where this flow would actually fail. We won't be able to recover data using just this flow. So let's take the worst case example, right? So everything is pretty much the same. We have the chunk 8 KB. We want to write B into this. We take A, we get it into memory, right? We write B into the memory chunk. We commit it to the log, right? Now, after it has committed, we are kind of in the middle of writing this 8 KB chunk to the hard disk, correct? So it's an 8 KB write going to the hard disk. But unfortunately, this time we crash in between the middle of our write. So while we are writing the whole 8 KB, we crash in between that. So what happens is the data that was in this chunk, it could be A, B, it could be some metadata which is present inside that 8 KB. It could be anything that is only partially written inside the hard disk. It is not completely written. We don't have complete A, B inside it. We just have some partial data. Essentially, from the database point of view, this chunk has now become completely junk. We are not, it makes no sense to it. We need to kind of, now ideally the database would need to fix this. So let's see what the database would do when we go for a log recovery. So again, we see that our database is in an inconsistent state. We have the log here, and we see B needs to be written, right? Again, the database would find the original chunk in the hard disk, but this time what it would be doing is it doesn't know this chunk is also completely junk, right? So it gets this chunk from hard disk to memory, and then it tries to write B into this chunk that is corrupted. So as you can see, if you write B into something that is junk, we end up with more junk. And that's how we end up with a database that is just silently corrupted. Your database would tell you, okay, everything went perfectly, the log is recovered. You would be happy, database is happy, but actually the data is completely corrupted for you. Anything from this point on is just, you're just modifying a corrupted database. And I'm sure all of you can understand why this is such a critical problem, especially with sectors like finance and which have critical data inside them. So obviously this is not something that our production databases can tolerate. So what have they come up with, right, to tackle this? So what they do is something called, in Postgres, it's called full page writes. MySQL has a similar concept. I think they call it double write buffering. But yeah, the idea is pretty much the same. What we'll do is, again, let's look into the whole insert B into the table and the crash scenario. So we'll get the disk, we'll get it into memory, we'll write B into the chunk. This time, if you concentrate on the log, this time you'll notice that it's different. What we do is we don't just write B into the log, we write the initial state of the chunk as well. So the whole 8 KB, instead of just a few bytes of B, we write the whole 8 KB inside the chunk, and then we write B and commit. And then again, we are writing it, and the worst case kicks in, we crash in between, we have junk, right? So now I think you'll get an idea of how this is useful, right? So this time, when the database tries to recover, it will notice that, okay, there's something in the log. Now, the difference comes from here. Instead of looking at the hard disk to get the initial chunk, it knows that we have written the initial clean state of that 8 KB inside the log itself. So, so you can see it will get the initial state from the log, write B into it, and write it to the hard disk eventually. And through this, even though our actual hard disk 8 KB chunk was junk, the database is able to recover from it, and we have all our data back. It's in a consistent state. Everyone's happy. But I'm sure you can imagine the overhead that this thing brings in, right? Because after every checkpoint is what we call it. After every checkpoint, the database would be writing an extra 8 KB. And if you are running at a really big scale where you have millions of transactions going on every minute, you can't just be writing 8 KB every time. But that's exactly what we do right now. And that's exactly where a lot of performance of our databases go, just because it can't tolerate the corruption of the page while being written to, right? So let's see, now that we have discussed this, let's talk a bit more about when the page can get corrupt. So we said that when the 8 KB chunk was getting written, if we crashed in between, the page got corrupted. But why is that the case? Why did it get corrupted? So let's talk about that. So if you look at the top red box, that's our 8 KB chunk, right? Now we need to understand that the underlying disk can't has some constraints, right? Usually these days, most of the disks have a limitation of 4 KB of write that they can do at a time. So that is to say, if we ask the disk to write 8 KB onto it, it will have to do it in two operations, right? So it will first write the initial 4 KB, then it'll write the next 4 KB. And that is where the non-atomicity comes in, right? So what happens is we are sending an 8 KB, right? We have written the first 4 KB, but then we crash. And this results in half of the 4 KB being new, but the other half is still old. And this kind of creates an inconsistency in the database, right? So this is what we call non-atomic behavior. Basically, the fact that our 8 KB is not written in one go makes it non-atomic. In other words, a write will be said to be atomic when if that write can either complete fully, or if it fails, the old data is completely as it is. We can't have like half write successful and half write unsuccessful. So if you look at the diagram, the above two options, the above two scenarios are kind of an atomic write after crash. So after crash on the left side, it would either have completely old data, or as depicted on the right, it would have completely new data. Similarly, if you look at the non-atomic examples at the bottom, after crash, either the left side would be new and the right half of the data would be old, or vice versa, right? So that is the difference between atomicity and non-atomicity. And the fact that our IO stack is non-atomic at this point, that is the reason databases have to do all these double writes and all these extra buffering that is causing them performance degradations. And but that is also important for data integrity, because the whole stack, including the hard disk, a lot of them these days don't offer atomic behavior. But that's changing, and that is what our talk is about now. Basically, we kind of want to talk about how we so now that we have discussed what atomic rights are, we want to talk about how we went about enabling atomic rights and what work the community has done in this area. So I think Ritesh can take you through some of the initial concepts of that. Over to you, Ritesh.
Sure, thanks, Ojaswin. So let's discuss the construct of atomic rights in Linux kernel, and so basically Linux today does not have the support of atomic right, and I think we will go over this slide first, like to just cover the concept of how IO stack looks like, right? So I mean this diagram, if you see, it basically shows from the user space to the disk. It shows various layers of IO stack. For example, you have VFS. When you submit a write request from user space, you first use, say a write call or a p write call. Comes to VFS, then you have your file systems, and then you have a block layer, device driver, and then eventually your disk actually. So in like most of the two of the most common two of the most common paths to be used is direct IO and buffered IO. Buffered IO uses the page cache, and whenever, let's say, the data the write request comes, the data sits into the page cache, and whenever, let's say, the write back or a sync call comes, fsync call comes, the dirty data is actually flushed to the disk. And then you have a direct IO where directly the user space buffer gets written to the disk actually, and it bypasses the page cache. Right. So this is like a general IO stack, and the reason for showing this entire IO stack is that we will eventually go through each and every layer of this, and we would basically talk about that the support of atomic write is required. All these layers require changes to be made to support atomic writes. And yeah, we can go to the next slide. So yeah, so this essentially covers the changes that are required, right? Like from the example, for the user space needs to know whether your Linux, the Linux that you're using supports atomic writes or not, right? And then in the file system layer, there needs to be changes with respect to how you are doing an allocation, whether your allocation are following the constraints of atomic writes or not. It needs to be aligned properly and all, right? And then in the block layer needs to respect that whether the BIOS can be split or not and merged or not. And these are the things that we will go through. But then at a high level, all of these layers need support of atomic writes, and eventually there also needs to be hardware support. So for example, you have devices, storage device, which would need these capabilities to support atomic writes. Right, so we can go to next slide and which cover each slide in detail. So let's cover through storage devices first, right? So in market we have both SCSI and NVMe standards, and they both have in the specs, they have sections in the specs which talks about what are the constraints required for atomic rights, and some of these are not common. Some of these constraints are common. For example, SCSI has requires a separate atomic right command. If you see in the SCSI at the end, it requires a separate atomic right command, but NVMe does not have any special command for that. But otherwise, there are other changes. For example, you have a maximum atomic right size. There is a concept of alignment, like your offset should be aligned, like your physical offset at which the write is going should be aligned, and then you have a concept of boundary, so that your atomic rights, your write should not cross a specific boundary specified by the device, and things like that. So these are some of these common things between SCSI and NVMe, and there are some other constraints as well which NVMe does not restrict us, but then SCSI has special commands like special atomic right command. So that is what, like, so once you have a device which is atomic right capable, that is where the changes in the various layers of Linux stack will be useful, so that the databases can eventually use this to support atomic rights and kind of disable the full page write, or other features in their databases, which Ojaswin just explained. So let's talk about device driver layer, right? Like, so in the device driver is basically trying to expose the constraints of both NVMe and SCSI in a way so that the user can actually know what is the minimum and the maximum supported atomic write lengths, so that whenever we prepare the buffer and submit it, we can follow the constraints of what the device requires us. And then there are also some some constraints introduced, which is, for example, write should be a power of 2. The length of the write should be a power of 2, and it should be naturally aligned. And I think this is mainly to make sure that we have a common sort of changes to satisfy both the constraints of NVMe and SCSI. Now, so this is what. So there are changes that are done at the SCSI and the NVMe layer. With respect to what has happened in the community, I think we will speak about it at the end. But these are the changes that are required from, say, device driver side first, and then let's talk about the kernel block layer, and we will talk about what are some of these limitations of what block layer imposes. So let's talk about the current working of block layer, right? So for example. The file system will submit a struct bio as a unit, which block layer accepts it from the FS layer, and it works on the struct bio, right? So what struct bio eventually has is like, where is your data sitting into memory in DRAM, and at what sector of the disk you want to do this write to, and what is the length of your write. That's like at a very high abstract level. That is what your struct bio contains, and that's what is passed to block layer. And then block layer can do various things, actually, as we know. So what block layer can do is, for example, it can split these BIOS into multiple different BIOS if, let's say, the device have a constraint of what max write can actually go through. And then it can also rearrange the BIOS. Like, for example, you have an IO scheduler within block layer which can actually do a rearranging of BIO. It can actually merge multiple BIOS into one and create a new BIO, right? So this splitting, merging sort of things are not really like we need to be very careful about, and the block layer require these changes to make sure that Linux gets an atomic write support, right? So there will definitely be changes required in the block layer for that. Yeah, so let's talk about one other special one, like a very common constraint. For example, when you have multiple small bio requests coming from user space, and let's take at step 1 here, right? If you see let's say our atomic write can only support up to 128 sectors at a time. This is just a just as an example, we are considering one of the common problem that exists with current block layer. So let's say 128 sectors is the maximum supported atomic write from a device. And let's say if in the request queue you have one bio, which is, let's say, at a start sector of 64, which is an atomic write which is submitted by the user, and your length is also 64. So let's say this is already following the device constraint. So the user has taken care of the device constraints properly. And then let's say in step 2, what the block layer can do is it can actually see these two different BIOS, and then it can actually merge them into a third bio in step 3. If you see it, it can eventually merge it, and then will make it start sector 64 and length becomes 192. Now this length of the entire write is more than what your device can actually do a write with atomicity followed, right? So these are some of these um, some of these things that block layer currently does, and it needs to handle differently for atomic write. So there are some changes definitely required in the block layer as well. Yeah, so that's all that. Now, similarly, the third constraint, like we can split the BIOS as well. So if you have, let's say, a 64 KB of atomic write, and then let's say if the block layer decides to split it because your device doesn't support, let's say, that much of that big of an atomic write. Just for an example purpose, but it can actually split it into two BIOS, which is 32 KB each, right? And then that makes the original write not atomic anymore, because the user wanted the entire 64 KB to be written, let's say, in one shot, but then block layer ended up splitting because of some constraint, let's say the device offers with respect to, let's say, the maximum number of segments are exceeding, or things like that, right? So splitting, merging, rearranging are some of these common things in block layer that needs to be handled in a specific manner, so that like in a different way for atomic write is what we would say. Now let's discuss the kernel VFS layer. So we are going from bottom up the stack because the storage device is where the hardware constraints comes up, and then we are now going up the stack. Let's discuss the VFS layer, and then we can discuss the file system layer. So if we discuss the VFS layer, right? So VFS is a common interface. VFS actually defines the interface for both the file systems and for how users should interact with the Linux as well, right? So there are some challenges in implementing atomic DIO writes, and for example, like you need to advertise all of these constraints that the hardware device comes up to a user space in such a manner that user space can actually see what are the constraints needed to be followed, so that it can submit a write which is like and can do an atomic write. So, and then there are, as we saw, there are two specs, SCSI, NVMe, and things like that, right? So we need some kind of a common interface so that the user can understand and should be able to perform atomic writes. So let's go to the next slide. And so what I think community has discussed and come up with is a pwrite v2 system call can be used. Pwrite v2 also supports a particular flag as well in the system call. That means that we can actually have RWF atomic flag defined, and it becomes a property of a per write call. So that, like, we can define that whether this write is an atomic write or not using this flag RWF atomic. And then we have also used statics. Statics is like, get file statistics for like an extended file status, basically, right? So with statics, we can define what are the min and the max limits, and that the device puts a constraint, and using those limits, the user can actually submit the write within that limit, so that it can actually support atomic write, right? And that's a common interface that is required at the VFS side layer of changes, and then we can look into the file system. Okay, so before that, so this is a very small pseudo code just to explain like how the changes would be eventually, right? So once you have a static system call, you could get the the min and the max value, and that also, I mean, like using statics, you can also see whether your underlying device supports atomic writes or not. And apart from that, you could also get min and the max value, and then you can look into what would be the write length, so that it supports both min max within the min and the max boundary. And then we can do a pwrite v2 call along with RWF atomic flag set, and that would basically make a write call to the Linux to basically do atomic writes. Yeah. So Ojaswin will take over. What are the changes required for file systems? Say, for example, for ext4 for doing this atomic writes.
Yeah. Thanks for the overview, Ritesh. Um, so yeah, so we saw the different changes that are needed and different challenges we faced implementing atomic writes in various stacks. So let's see on the file system layer what atomic writes, what does it mean to have atomic writes, what are the changes needed, and to understand that we need to understand how block allocation works in the file system, because that is one of the biggest challenge in the file system layer to implement atomic writes. So let's just go briefly through what block allocation is in file system and how does it affect atomic writes, right? So let's see. So I want you to focus on the upper half of the diagram. I know it's a bit crowded, but yeah. So let's look at the step one. So there's a file and there's a user. The user wants to write 8 KB to a file, and file systems usually work on a minimum block size. So it's commonly called block size of the file system. Usually, most of the file systems that we see around ourselves use a 4 KB block size. That also happens to be the page size of x86 systems. There's also a constraint that the block size can't go beyond the page size. So yeah, but yeah, coming back to the example, so we have this file. The user is trying to write 8 kbs to it, right? So inside the file, the user is actually writing at 0 to 8 kb, right? So this 0 to 8 kb is what we call the logical offset, or the logical side of the mapping. This is not the actual blocks where the data will sit, but in that file, the user will see it as a write to 0 to 8 kb, right? Now it goes to the kernel side and reaches step 2. Now what the file system will do is it will go and scan the whole disk that you see in red, and it will try to find two blocks free, two blocks as in 4 KB, that is four blocks, 4 KB blocks. So it'll try to find two blocks. And in this diagram, we can see it finds blocks 151 and 152. So it says, okay, these two blocks are free. So let's assign that to the user, and it goes and then finally writes that 8 KB of whatever user has supplied to block 151 and 152 of the disk, right? So now this mapping of files 0 to 8 KB logical offset to block 151 and 152 on the disk, that is the physical offset as we call it, is actually maintained by the file system. And that is one of the major roles of the file system, to kind of maintain where each file's data sits on the disk, right? And and one more thing that is important to note is that the user does not have any control over which blocks the user will get, right? So if you come to the bottom half of the diagram now, on the left side you can see I've just shown a lot of different valid mappings that the file system could have produced. So on the left side we see the mapping that we saw in the example, that is block 1 and 2 get 151 and 152 continuous blocks. Next to that, we see another valid mapping. The file system could have given block 36 and block 152. So it's not necessary that the blocks would always be continuous. And on the right again, one more example where blocks 1, 2, 3 are mapped to 36, 152, and 153. Right. So these are the various valid mappings. The point being that the user can't control this, right? This is something that the file system allocation algorithms decide. So now where atomic write constraints come into play is that now these block allocator algorithms, up till now, the ext4 block allocator algorithm or even the XFS algorithm as such, are not aware of atomic constraints, right? So say if you have a device that wants your writes to be at certain alignment or certain offset, things like that, or not cross certain boundaries, the file system doesn't, the block allocator doesn't take that into account, and the user doesn't have any way to indicate to the block allocator that, okay, I need 4 KB aligned blocks, or I need 16 KB aligned blocks, or I need 32 KB aligned physical blocks on the disk. And that's where the issue comes in. So the user might be trying to do an atomic write, but then the file system will go and give the user discontinuous blocks. And obviously, if your blocks are discontinuous, you'll never be able to do it in one shot. You'll always have to, like, go, say if you get two blocks, that are separate, you'll have the device will take 2 turns to write it, and again the atomic IO will kind of split into 2 operations, which we don't want. So that is the kind of challenge in the file systems in the block allocator that is introduced when we try to enable atomic writes in file systems. So let's go briefly through how we try to solve these in ext4. So in ext4 there are 2 approaches that we have explored to solve this challenge, right? So one is a pre-existing feature that exists in ext4 called big alloc. So what it does is, as I said, the file system allocates in the blocks of 4 KB if the block size is 4 KB, and it can't go beyond 4 KB because it's usually limited by the page size of the machine, right? What big alloc does is it kind of tells the file system that now the minimum allocation unit will not be 4 KB, it will now be 8 KB or 16 KB. We can configure that, but that is what big alloc does. It indicates to the file system that now you will only have to allocate in bigger chunks. So how that helps us is, say if a device requires 32 KB alignment to do atomic writes, say the storage device is such that we need a 32 KB alignment. Now what we can do is we can make a file system with big alloc and set the big alloc size, or the cluster size as we call it, to 32 KB. So now every chunk that file system allocates will always be in 32 KB limit. So it can allocate 0 to 32 KB, and then it can allocate 32 to 64, and so on and so forth. So the physical blocks that you get will always be aligned to 32 KB, because that becomes your minimum unit size when big alloc is enabled. So this is a pre-existing feature. There are different use cases for big alloc, not necessarily just for alignment, but it's easy to integrate with atomic writes since it already exists. So we try to explore with that, and we were able to actually get atomic writes working with big alloc, and the alignment just worked. The only issue with big alloc is that it's very restrictive. So if you have a file system that is not big alloc enabled, and now you want to enable big alloc to do atomic writes on it, you have to completely scrap that file system, make a new one, and do a big alloc on enable big alloc on that, because you can only enable this feature during the file system creation time. You can't do it during runtime. So that makes it pretty restrictive, and it's like it's not an ideal approach. It's a good first approach, I would say. Maybe it's good for some use cases, but yes, we need a bit more fine-grained control, and that's where the second solution comes in, which is adding aligned allocation support in ext4. So it's kind of saying that, why instead of using big alloc, why don't we just make the allocator smart enough so that the user can somehow indicate an alignment to it, and it will just give the blocks on that alignment. And this can then become a per write feature for the allocator, or a per file thing, and it's pretty flexible. You can do some allocations that are aligned, and then do some allocations that are just normal allocations. So you don't need to have a file system wide feature just to do a few atomic writes. But yeah, the problem is that the changes are a bit more involved. You're changing the allocator, and it becomes a bit more complex. We have kind of explored this as well. We were able to get it. We were able to get the changes in the allocator to and get them working with atomic writes. But this is still kind of in review in the community. Um, yeah, this is the next logical step, and something that we are exploring. Now, while we talk about different allocator changes, I think it's also good to mention that there are some systems, unlike x86, which can have page sizes which are much more greater, 16 KB or 64 KB, such as PowerPC, which can have a 64 KB page size, or even ARM, which can have 16 KB or 64 KB page size. So now, how these systems benefit atomic writes is, when you have a 64 KB page size, you can actually create a file system that has a block size bigger than 4K. So you can create a file system with a 32 KB block size using the command that we showed in the first bullet point at the bottom. That is mkfs.ext4 -b, and then you give the block size. And since the block size is still less than page size, it just works. And as soon as you make the block size 32 KB, all your allocations will be 32 KB aligned, and you kind of get the benefit directly straight out of the box. So that's also a good thing if you have access to such systems and if you want to play with atomic rights on such systems. So we have posted changes. We have posted the patches for the big log integration with atomic rights and the atomic right interface in ext4, as well as aligned allocation interface with atomic rights as well. And they're still kind of in discussion, but yeah, the community, we are still working on that. So yeah, so that was the changes we made on the ext4 side. Kind of now to summarize everything, to give you an idea of what it took to just get atomic rights working in the kernel IO stack. We have the summary slide here. You can see on VFS side, we had to come up with an interface. The community decided PWrite v2 was good for this, and then how do we expose the capabilities of the device to the user? We got statics for that. On the file system, we worked on block allocator changes so that it can respect atomic right constraints, and also we explored big log. On the ext4 side, the xfs side is also being explored in the community. They have also come up with similar solutions to get atomic rights working. On the block layer, again, as Ritesh discussed, we had to take care of merging and splitting. That again we did by adding intelligence to the merging algorithms and by exposing min and max in such a way that you'll never split the BIOS. The APIs needed to be defined so that we can hide all the underlying device complexities from the user, and the device drivers had to expose the capabilities. Coming to the future work, yes, there's a right now we talked about direct IO path, but there's also active interest in supporting atomic rights in buffered IO. Although it's a bit more challenging to get it right, because I think, as Ritesh pointed out, buffered writes also involve page cache, and they have a um, a bit more complexities in them, because when the write is actually being performed, all the data about how much the user wrote and what the user's intent was, which part is atomic, which is not, these kind of information is lost. So there are some added complexities, and it's also something that will be discussed in upcoming LSFMM. The proposal details can be found in the reference link. And yeah, but with the good thing is, with direct IO, MySQL can benefit the performance benefit with atomic rights. With buffered IO, database like Postgres can benefit with it, because that it primarily uses buffered IO for its working. Yeah, so with that, we will just go through the current state of atomic affairs in the community. So yeah, the interface of atomic rights, the direct IO changes, the device level, and XFS changes have been posted by Oracle. They have taken the initiative to post them. And we are still going through community review, but I think everyone in the community agrees that atomic rights is something really great to have, because of the improvements it kind of brings to the table for different database workloads, right? Um, so moving on the ext4 side, it's something that we have been primarily focusing. We have posted a couple of POCs, both exploring the bigger log side of atomic rights, also building upon the interfaces of atomic rights of the block layer to integrate them with ext4 and to get them all working. We have also posted another patch set that kind of makes the changes in the block layer, makes the changes in the allocator, makes it intelligent so that the alignment can be taken care of. Basically what we discussed in the challenges field. So that's all posted. You can, all the links are in the reference slides, and you can always go and have a look. Or yeah, so this is just the legal statement that we kind of have to show. And thank you everyone for attending our talk.
Thank you.
Yeah. Hope to see you next year in person.